Welcome to chapter 13. Okay, so chapter 13 is about gas laws and kinetic theory. So for first subtopic 13.1, we have ideal gas equations. Let us look into example 13.1. A volume of vessel A is 3 times to the volume of vessel B. The vessels are filled with an ideal gas and are at a steady state. The temperature of vessel A and vessel B are at 300 Kelvin and 500 Kelvin respectively, as shown in figure 13.2. Okay, if the mass of the gas in the vessel A is m, obtain the mass of the gas in the vessel B in terms of m. Okay, alright, let us look into solution. So for the initial information, okay, so we know the relationship between volume of vessel A and vessel B, okay, and then the mass, okay, at vessel A given as m, and then the initial temperature, okay, initial temperature A and B. Okay, since the vessel A and B are connected by a narrow tube, okay, so thus the pressure for both vessels will be same. Okay, pressure at A and B same. That means let's say we put it as a common symbol P. Okay, the system is in the steady state. Okay, therefore initial temperature, okay, given, and by applying the equation for the state of an ideal gas, okay, which is equivalent to PV equivalent to nRT, and whereas N, okay, number of mole will be equivalent to mass over molar mass. Okay, replace in and expand the equation. Okay, so therefore for vessel A, we replace in to obtain equation for vessel A. And then, so since the relationship is already given, so replace in the value for the vessel A. Okay, so we end up with equation 1. Okay, and then do the same thing for vessel B to obtain the equation. Okay, and then what we can do is that we can solve it simultaneously, equation 1 and 2. Okay, so since PVB equivalent to PVB, replace in, okay, find the mass of the vessel B in terms of m, okay, which will end up with m over 5. Okay, for example 13.2. Okay, 13.2, you have a connecting tab in between vessel B and A. So refer to figure 13.3. Initially A contains 3 meter cubic of an ideal gas at temperature 250 Kelvin and pressure given 5 times 10 to the power of 4 Pascal, while B contains 7.2 meter cubic of the same gas, okay, at 400 Kelvin and 2 times 10 to the power of 4 Pascal. Calculate the pressure after the connecting tab has been opened and the system reach equilibrium. Assume that A is kept at 250 Kelvin and B is kept at 400 Kelvin. Okay, so for solution, okay, initial volume we have, okay, initial temperature we have, okay, and then initial pressure of A, and then the initial volume, okay, and then initial temperature of B, and then the pressure of B, okay. After connecting, the tap has been opened and the system reached equilibrium, so therefore the pressure will equalize, okay, so that means we will have same pressure. Okay, by using the equation set for an ideal gas, okay, PV over T, so P naught initial, V naught initial over T naught, which will be initial, where P1 V1 over T1, which will be the final pressure, volume and temperature. Okay, so initially we have two vessels, vessel A and vessel B, and finally we will have also two vessels. Since the tap has been opened, it will have common pressure. Okay, so that means we can factorize the final pressure. Okay, so we already extracted the information, replace in, okay, and then solve it to find the final value of P, okay, which will end up with 3.2 times 10 to the power of 4 Pascal. Okay, so next subtopic will be on kinetic theory of gases. Okay, so for example 13.3, we have 8 gas molecules. Okay, 8 gas molecules chosen at random are found to have speed of 1, 1, 2, triple 2, and 3, 4, and 5 meter per second. Okay, so over here they wanted to determine the mean speed of the molecule, the mean square speed of the molecule, and then the root mean square speed of the molecule. Okay, so for the solution, okay, number of atom, okay, we have 8 lah, okay, 8 gas molecule. Okay, so to determine the mean speed, okay, just calculate the total speed and then divide by number of molecule. So that means basically what we do is that we find the average, okay, so which will end up with 2.5 meter per second. Okay, and for mean square speed, okay, so for mean square speed, what you need to do is that you need to determine the summation of the square value, okay, and then divide by the number of molecule. Okay, so we square the value for each velocity and then divide by the total number of molecule, so which will end up with 8 meter square per second square. Okay, and then for the root mean square, okay, so we already have the square mean square speed. Okay, so what you need to do is just determine the root mean square value. Okay, root value of 8, which will end up with 2.83 meter per second. Example 13.4. A cylinder of volume 0.08 meter cubic contains oxygen gas at the temperature of 280 Kelvin and pressure of 90 kilopascal. Okay, they wanted to determine the mass of the oxygen in the cylinder, the number of oxygen molecules in the cylinder, and then see the root mean square speed of the oxygen molecule in the cylinder. Okay, so given over here constant R, K, K, and then the molar mass given 32 gram per mole, and then the Avogadro constant. Okay. Okay, so for the solution, we have the value of the volume, temperature, and also pressure. Okay. Okay, by using the equation PV equivalent to nRT, okay, where N will be equivalent to mass over molar mass. Okay, expand the equation. So replace in the value. So once you solve it, we can determine the mass of the gas, which you should end up with 9.9 times 10 to the power of -2 kg, kilogram. Okay, question B, the number of oxygen molecule in the cylinder. Okay, what we can do is that you can determine the number of mole, which is equivalent to the ratio of mass over molar mass, number of atom over Avogadro constant. Okay, so just rearrange the equation, and then mass over molar mass times with the Avogadro constant, we will end up with the number of molecule, which will be equivalent to 1.86 times 10 to the power of 24 molecules. Okay, see the root mean square speed of the oxygen molecule. Okay, for to determine the VRMS, we can use this equation. Okay, root value of 3RT over M. Okay, so replace in the value, which will end up with 467 meter per second. Example 13.5. Okay, we have a vessel which contains hydrogen gas 2.2 times 10 to the power of 18 molecules per unit volume, and the mean square speed of the molecule is 4.5 km per second at the temperature of 50 degrees Celsius. They wanted to determine the average translational kinetic energy of a molecule for hydrogen gas, and then B, pressure of the hydrogen gas. Given the molar mass of hydrogen gas, okay, given 2 gram per mole, okay, Avogadro constant given, and then constant K is given, okay, and then information available from the question, okay, number of molecule per unit volume, okay, and then the mean square speed of the molecule, okay. So this one given in kilometer per second, convert into meter per second, okay, and also temperature given in degree Celsius, also convert into SI unit, which will be in Kelvin, okay. So for the average translational kinetic energy, okay, KTR will be equivalent to 3 over 2 constant K times T, okay, just replacing the value, so which we will end up with 6.69 times 10 to the power of negative 21 joule. Okay, so for B, pressure of hydrogen gas given by equation 1 over 3 N over V, okay, M times V square, okay, mean square average value, okay, and then where mass will be equivalent to molar mass over Avogadro constant, okay, we rearrange, okay, substitute in over here, and then replace in the value, okay. So once we solve it, we will end up with pressure which is equivalent to 1.1 times 10 to the power of negative 5 Pascal. Okay, now let us look into example 13.6. A vessel contains an ideal polyatomic gas at temperature of 30 degrees Celsius. The total translational kinetic energy of the gas molecules is given as 6.00 times 10 to the power of negative 6 joule. And then the mass of the gas is then doubled, and the total translational kinetic energy of the molecule becomes 13 times 10 to the power of negative 6 joule. Okay, they wanted to determine the new temperature of the gas. Okay, so these are the initial information that we have: T1 initial, okay, E1 initial, and then E2, okay, final, and then the mass becomes double, M2 becomes twice the value of M1. Okay, so we can apply the equation of the total translational kinetic energy, so which will be equivalent to 3 over 2 nk T, and where n will be equivalent to the ratio of mass over molar mass times Avogadro constant, okay, and also K will be equivalent to ratio of R over Avogadro constant, okay. So replace in the value, okay, expand, then simplify, which will end up with 3 over 2, okay, mass over molar mass times constant R times with T, temperature. Okay, so since now we have two temperature, what we can do is that we can form one equation for T1, okay, which will end up with E1, and then another equation for T2, okay, which will be amount of energy E2. We end up with equation 2. Okay, so what we can do is that we can solve simultaneous. So over here we use the approach of division. Okay, equation 2 divide with equation 1. Okay, so simplify it. So the final answer we will end up with 328 Kelvin. Okay. Okay, so for the last subtopic, let us look into internal energy. Okay. So for this one, we have one example, which is example 13.7. We have 2 moles of an ideal monatomic gas in a closed container at constant volume heated until its pressure is doubled. Okay. If the final temperature of the gas is 750 Kelvin, calculate the initial temperature of the gas and then the change in the internal energy of the gas, okay, given value of the constant R over here. Okay, so for the solution, okay, we have number of mole, okay, 2 mole, and then the pressure becomes double, okay, and then the final temperature, okay, which is 750 Kelvin. Okay, so we can apply Gay-Lussac's law to determine the initial temperature. Okay, initial temperature over the ratio of the initial pressure over initial temperature, which will be equivalent to final pressure over final temperature. Okay, so replacing the value, so therefore initial temperature we will end up with 375 Kelvin. Okay, and for the change in the internal energy, okay, final energy minus with initial energy. Okay, expand the equation. So therefore F over 2 and R, which will be constant. So the changes is that we only have changes in the temperature. Okay, delta T only. So rotation or degree of the freedom will be 3. Okay, 3 over 2 mole 2. Okay, constant R. Final minus with initial temperature, we will end up with 9.35 times 10 to the power of 3 joule. Okay, so that's all for this chapter. Have a